Alright, here's an interesting exercise. So they introduced this interesting idea called asymptotic density, which I think is like a thing in probability theory, and this sort of has like a bit of an ergodic theory flavor to it, potentially. I'm not entirely sure though. Um, that's sort of the context I've seen it come up in before. But I also don't really know a ton about ergodic theory. Anyways, so um, is this set of is the collection of sets for which the asymptotic density exists a sigma algebra or an algebra, or is it nothing? And spoiler alert, it's nothing. But actually, let's go ahead and prove some things. Well, the first thing I notice is that it's closed under complements, and even though it's not going to end up being a sigma algebra or even an algebra, um, we can still prove that it's closed under complements, even though that doesn't help us arrive at anything else. So, suppose we have a set A in script A. Let the limit as n goes to infinity of, you know what? Let's just call f sub a of n. This is going to be a intersected with the integers from 1 up to n. Over n. Because I'm going to be writing this a lot, and I don't want to have to write it a lot, so I'll just call it f sub a of n. Okay. So the fact that a is in the set A is in the collection script A means that there exists some number theta such that the limit as n goes to infinity of fan is theta. For each n, note that fa of n plus fa complement of n equals 1. And that's because if you add these two things together, then you have a intersected with the integers from 1 to n, the size of that set, plus the size of a complement intersected with the integers from 1 to n. And any integer is either going to be contained in a or not contained in a. Every integer between 1 and n is either going to be an a or it's not. So it's either going to be an a or a complement. So if you add those two norms together, you're going to get all of n. And so you end up with n over n, which is 1. And so let's see here. So if we look at f of a complement of n, then this is just 1 minus fan. And so then you just take the limit as n goes to infinity. Facn is going to be 1 minus the limit as n goes to infinity of fan. So this is just 1 minus theta. Thus, if a is in script A, then a complement is in script A, because the limit as n goes to infinity of fa complement n also exists, and in particular it's 1 minus theta, where theta is the limit of fan. Okay, so we have closure under complements. To prove that script A is not a sigma algebra, and this one I was actually able to think of this on my own. Basically, the idea is you find a set which is not contained in script A. You find a subset of the natural numbers. Here, this is equal to the natural numbers, because I don't put 0 in the natural numbers, because I don't want to. It seems like more of an analysis thing to not include 0 in the natural numbers. So to prove that A is not a sigma algebra, what we're going to do is we're going to find some subset of the natural numbers which is not contained in script A, and then we will construct it as a countable union of elements in script A. And you basically do it just like one integer at a time. So to prove A is not a sigma algebra, suppose A is in N, but it's not contained in A. So let's come up with an example of this. For example, exclude the... So this is just like a simple idea of like, what would you do if you wanted to construct an example of a subset of the natural numbers which is not in script A? Exclude the first N1 positive integers, I'll say natural numbers, from A. So we're going to exclude a bunch. Then include the next N2 natural numbers. I'll just say numbers. And you keep adding things in until f sub a of n1 plus n2, because if we add the next n2 numbers after n1, then we're obviously now at the n1 plus n2 integer. So this, we want this to be at least 1/2. Then exclude the next n3 numbers until fa of n1 plus n2 plus n3 is less than or equal to 1/4. Then include the next n4, and maybe at this point you can see where we're going with this, the next n4 numbers until fa, and I'll just do the sum from 1 to 4 of ni, is greater than or equal to 1/2, and then we'll continue. So we'll exclude the next n5 numbers until fa of n1 summed up to n5 is less than or equal to 1/4. So, for example, let's say we could do A to be, let's exclude 1 and 2, and then include 3, and then 4. And then at this point, fa of 4 is going to be 1/2. And so we'll start excluding numbers. So if you go all the way up to 8, and then let's see here, fa of 8 is going to be 2 over 8, which is 1/4. And so at 9, we start including things again. So I think 9, 10, 11, 12, right? Because once we get up to 12, then we have 6 elements in A. So fa of 12 is going to be 1/2. And so then you start excluding again. And so I think you just exclude the next 8 numbers. And so you'll get up to 20 and then 20. Right, because at 20 you have 6 over 20. No, I guess you'd go beyond that. So you want 6 over 24 is 1/4. Right? Okay. So let's see. If we have this set so far, then f sub a of 24 is going to be 6 over 24, which is 1/4, because 6 times 4 is 24. Right. And so then you go 25, 26, 27, and you continue this. So as n increases, fa of n by construction oscillates between 1/4 and 1/2. Now it might go a little bit outside of those, particularly if we like skip odd numbers. But the amount that it goes it doesn't really matter. The point is, regardless of that slightly potentially going over 1/2 or under 1/4, it still holds that the limit of FAN does not exist. And thus, A is an element of, let's see here. So I guess technically A is an element of the power set of N, but not an element in A. Alright, so this is what we want. Okay, so let AI, my computer's freaking out, let AI be the singleton set consisting of the ith element, or the ith integer, in A. So A1 is the singleton set. For this particular example, A1 consists of the integer 3, A2 is just the integer 4, A3 is just the integer 9, etc., etc. Then the limit as n goes to infinity of FAI of n, well, once n passes beyond the ith integer of A, then the numerator of FAIN is always going to be 1, and so this is going to be the limit as n goes to infinity of 1 over n, which of course is 0. So AI is in script A for all I. However, A is the union from I equals 1 to infinity of AI by construction, but this is not in F. Wait. I'm thinking the previous problem I just did. This is not in script A. So, thus, A isn't a sigma algebra. Alright, so there you go. Because it's not closed under countable unions. Okay, so it's not a sigma algebra. And then the next question after this is it an algebra? And I thought about this a little bit, and I was sort of on the right track. I was thinking, well, if it's not an algebra, then maybe there's some thing that we can do with this set A that we've constructed, some way to sort of break it up in a way that allows you to use it to prove that you don't have closure under unions. And I thought about it, and I wasn't really able to come up with anything, so I actually ended up looking on Stack Exchange, and I found an explanation, and I was sort of on the right track. You can take this example A and break it up in a way that lets you show that script A is not closed under intersections. And then you can deduce from there that it is not an algebra. So let's do this. So now we're going to prove that A is not an algebra. So we're going to let A be the even natural numbers. Okay, and now we're going to introduce two sets, B0 and B1. Let B0 And we're going to construct this using the things that I used to construct A in the previous example, in the previous paragraph. Let B0 consist of the even numbers between 1 and n1, between n2 and n3, etc. So for example, B0 in the previous example would be, let's see here, so between 1 and n1. So let's see here. So we exclude the first n1 natural number. So 1 and 2 are excluded, so we include 2 here. And then we don't include anything between n1 and n2, so we don't include anything between 3 and 4. But then between, I guess, no, we don't really have, I was thinking, do we have to worry about the endpoints here? No, we don't really have to, because the endpoints are either going to be odd or even, so that will sort of take care of itself. So then we go between 4 and 9, we choose all of the even numbers, so we have 4, 6, and 8. And then we don't do anything between 9 and 12. And then we do all the evens between 12 and 25. And so we do 12, 14, 16, 18, 20, 22, 24, etc. And yeah. And so basically what we see happening here is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not exactly even, but this is still oscillating. If you look at FB0 of n, you're still approximately oscillating between, let's see here, 1/4 and a half still. Does that make sense? Wouldn't it? Something about that doesn't seem right. Oh no, no, that's still what's happening, because you're including the gaps that are in A. And so this makes sense. So yeah, this still is going to oscillate between 1/2 and 1/4, approximately. Of course, this only goes up to, I think it goes slightly below. Like, it doesn't quite go up to 1/2, and it doesn't quite go below 1/4. Right? Because if you look at FB0 of 8, then you've got 8, you've got 4. Oh, no, it gets there. What am I talking about? And then you go up to 24, and you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, when you go up to 24, then you've got 11 over 24. So you don't quite get back to 11. No, you don't quite get back to 1/2. Let's say you're at 12, you get 5 over 12. So again, you don't quite get back to, so you're 5 over, no, 1, 2, 3, 4, 5. Yeah, 5 over 12, so you don't quite get back to 1/2. I think I'd have to look at this in a little more detail for larger numbers to actually understand what's really going on here. But anyways, let B1 consist of the odd numbers between n1 and n2. Scroll down a little bit. Between, and then we go n3 and n4, etc. So for example, B1 is going to be, so we include all the odd numbers between N1 and N2. So all odd numbers between 3 and 4, so that's going to be 3. And then we don't include anything between 4 and 9. But then between 9 and 12, we include 9 and 11. And then we don't include anything between 12 and 25. But then we do include 25, etc. This is sort of weird. B1 looks smaller and B0 looks larger than anticipated. Maybe the endpoints are causing an issue. I'm not entirely sure. Anyways, I might come back to this and look at this a little bit more, but the idea here is correct. Okay, so then the limit then goes to infinity of, okay, let's do that. Between 1 and N1 minus 1, between N2 and N3 minus 1, etc. Between N1 and N2 minus 1, between N3 and N4 minus 1, etc. This will make the next part that I want to prove more evident. Okay, so let's redo this. So between 1 and 3, so just between 1 and 2, so 2. And then everything between 3 and 4. Okay, no, this would actually be N1 plus N2. And N1 plus N2 plus N3 minus 1, etc. And here we have N1 and N1 plus N2 minus 1 between N1 plus N2 plus N3 and sum from 1 to 4 of Ni minus 1, etc. Okay, so now let's look at this. So, okay, I need to go back. So here's what I need to do. I need to label these things. 4, 5, 6. This is... We're doing a very concrete proof right now. This is absolutely not necessary to be going in as much detail as I am right now, and so feel free to fast forward if you would like to, and don't want to watch me do this. Okay, so we're going to exclude 1 and 2. So this is going to be N1, and then we're going to include 3 and 4. So this is N1 plus N2, so N2 is going to be 2. And then we're going to include 5, 6, 7, and 8. So 8 is N1 plus N2 plus N3, and N3 is 4. Then we're going to exclude the next 4. This is a sum from 1 to 4 of Ni. So Ni is going to be 4. Then we're going to, so 2, 2, 4. Wait, no. 4, 1, 2, 3, 4. 12 is the sum of the Ni's. And then 1, 2, 3, 4, 5, 6, 7, 8. Wait, 2, 3, 4, 5, 6, 7, 8. Should this be the next one? So let's circle the ones that we're including. No, we should go all the way up to 24. So then we have 6 over 24, which is 1/4. So this is going to be the sum from 1 to n of n5. No, of sum from 1 to 5 of ni. Then we include 25, 26, 27, 28, 29. So we've got 6. Go up to 30. So at this point we're on 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 30. 14 out of 32. 16 out of 34. 17. 18 out of 36. 18 times 2 is 36. So this is going to be the sum from 1 to 6 of ni. Okay, and then we do 37, 38, etc. Okay, here we go. So what's happening here? So B0 is going to consist of, so basically for all of the gaps where we don't have circles, we're going to include all the even numbers. So we'll include 2. We won't include 4. We'll include 6 and 8. We won't include 12. We'll include 14, 16, 18, 20, 22, 24. Okay, so there we go. Now B1, we're going to include all the odd numbers in the circled region. So we'll include 3. We'll include 9 and 11. We'll include 25, 27, 29, 31, 33, 35. So let's see what that's going to put us up to. When we go up to, let's see here. So B0, when we go B0 of 5, we're at 1/5. When we go B0 of 8, we're at 3/8. We go B0 of 12, or I guess 13, we'll get up to 3 over 13, which is like what? 0.23. So this looks like it's going between like maybe about 1/5. I don't know the specifics, and I guess if this were to be a truly rigorous proof, I would have to prove that these are oscillating. But the point is, B0 and FB0 of n and FB1 of n are going to oscillate. However, what about the limit as n goes to infinity? If B equals B0 union B1, then limit as n goes to infinity of FBn is going to be what? Well, we're in each of these gaps we have these intervals in the real line, and we're including half of the integers in each, approximately half of the integers in each interval. Well, actually, I think we are exactly including half of them. So like between 1 and 2, because each of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Each of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, each of these gaps appears to be an even number, and I'm sure there's a way to prove that that's always going to be the case, particularly since we started with an even number. So you're including, in each of these intervals, you're including half of the integers, so this limit is going to be 1/2. Of course, there will be some slight oscillations, but those oscillations will only be like one at a time. And so they won't matter in the long run. Because look, you've got like 2, 3, then you've got like 6, and then 8, 9. So you've got instances where like between these intervals of integers, you've got like you're putting in 2 things at a time. So there will be some slight oscillations, but because the oscillation is only going to be by like 1 at a time, it will even out as n gets really large. And so this limit is going to be 1/2. Okay, so this limit is 1/2. But notice that b0 and b1 are not in A. Well, the fact that the limit of... here, let's write this out. So b is in A, but b0 and b1 are not in A. And these are not in A because we've got oscillations. And the reason that b0 and b1 are oscillating when you look at fb0n and fb1n, they're oscillating for the same reason that A oscillates. Now, what the oscillations are between, I'm not entirely sure. I don't want to waste any more of your time by trying to figure that out on the fly, but it oscillates. I guess if this were like a proof that I were submitting for a class, I would want to go into more details there. Just going to put this so that's a sort of just a diagram. So yeah. So we have this. Okay. Now A intersected with B. Well, B consists of both B0 and B1. B0 only contains even numbers, and B1 only contains odd numbers. And A is the even natural numbers. So this intersection is just going to be B0, which is not in A. Since A and B are both in script A is not closed under intersections. I'll just say under and then the intersection symbol. Now, since A intersect B is equal to A complement intersect B complement, because if you want to distribute this complement on the right-hand side, you use De Morgan's, and then you end up with A complement complement intersected with B complement complement, which is just A intersect B. Any set, so this tells us that any set which is closed under both unions and complements is also closed under intersections. And since A is not closed under intersections, now we're just using the contrapositive of the statement I just said. A is not closed under both unions and complements. Hence, A is not an algebra. Despite the fact that it is closed under complements, it is not closed under finite unions. And so it would be nice to actually have an example of two sets which are in script A and whose union is not in script A, but I don't know of any. I mean, maybe you can construct one using these examples, but I'm not thinking of anything off the top of my head. The easiest thing, at least here, is to just do closure under, or prove that the set is not closed under intersections. And so, yeah, this isn't the best proof that I've ever given. Definitely, there's a lot of details in here that I skipped over, and a lot of details that I went into in this explicit example that I didn't need to. But I think math is very abstract, and like the deeper and deeper you go in math, typically the more and more abstract it gets. And so while you end up getting to things which are very advanced and it's very rewarding to see how far you've come, sometimes I get this feeling that things become less and less real because you can't really get your hands on things. But maybe that just means that you're proving things about things which are like more advanced. I don't know. But the point is, I think it's nice to have specific examples when you can. It's nice to be able to actually have an example and to see what you're doing. And I think actually being able to write out this example of B and B0 and B1, it's nice. But yeah, that's all we need to do for this exercise, or at least that's all I'm going to do. I'm not going to go into the details about like why specifically B0 and B1 are not in A. But yeah, after that, we're done with the exercise.